Previously, we were talking about operators, differential operators. In fact, and I told you how to write nth order linear differential equation. If we have given an nth order ODE, linear, in fact, linear ODE. We can write it in this form: an of x y or dny by dxn plus an minus 1 of x dn minus 1 y by dx n minus 1 plus so on plus a2 of x d2y by dx2 plus a1 of x dy by dx plus a naught of x y is equal to some function f of x. If this, I told you that if this function is 0, then this equation is called homogeneous. If the right-hand side function f of x is 0, then this ODE 1, for example, then this nth order linear ODE, this implies equation 1 is called homogeneous nth order linear ODE. If we introduce notations in order to simplify this notation, because we have to write a lot of things every time we write linear equations of this form. So we introduce that let D0 or D1, we start with D1, y is what? It is dy by dx, means first derivative, D1. If we have D0, then it's simply y. You can say D0 of y is y. There's no derivative here. And D2, y means d square y by dx square, second derivative, and so on. Dny is nth derivative of y with respect to x. If we use this notation, then we can write this equation in this form: an of x dn y plus an minus 1 of x dn minus 1 of y plus so on plus d2 of y and a2 of x plus a1 of x dy plus a naught of x d0 of y, or simply y is equal to f of x. So this is our equation 2. And further, we can take common y from all these terms, and we can write, in short, an of x dn plus an minus 1 of x dn minus 1 plus so on plus, d a2 of x d2 plus a1 of x d plus a naught of x is equal to f of x. So not f of x into, we put it in a bracket, into this whole thing is operated on y. It means if we multiply y on the left hand side with each term, we get the same equation equal to right hand side. This thing. Now, if we assume that this whole term, we call it an operator L. L. Okay, so L is what? L is this whole thing. An of x dn plus so on plus A naught of X. This whole thing is operator. Because this whole thing is linear, that is why we call it a linear operator. Okay. If there are no linearities here, then we cannot just take common y from each term. So the linear operators are defined differently, non-linear operators. This is how we can only define linear operators, okay? If we define this as an L, then this equation can be written simply as L of y is equal to f of x. Because this term operates on y, which produces f of x, then that is why we call it operator, because we are operating this thing on y. And if it is linear, then we call it a linear operator. Okay. Examples of this thing may be x square d square y by dx square plus 2x dy by dx plus or minus whatever 5y is equal to maybe x square or x square sine x. Then this equation simply can be written in this form: x square d square plus 2x d plus 5 into y is equal to x square sine x, where this is what? This is your operator, and it is linear operator. So the equation can be written in this form: L of y is sine x, this thing. Okay. Similarly, another example could be d square y by dx square minus 5 dy by dx plus 3y equal to 0 maybe. Is homogeneous equation, second order. It can be third order as well. D cube y by dx cube plus this thing. So it can be written as d cube plus d square minus 5d plus 3. Okay, this thing operates on y is equal to 0. So this is your linear operator. Okay, I hope you get it. If you have any question, you can ask me.
Sure.
Yes.
I just wanted to ask, like, what's the point of writing the operator like that when it's not like it's unique for every equation?
X is not unique for every equation?
No. Like, I mean, we're writing it as an operator, right?
Yes.
So, like, what's the point of doing that when it's unique for every differential equation? Like, an is going to be different for every equation.
Okay. We shall use this notation while solving higher order differential equations. Okay. We need it for the solution of. Till now, we have discussed the method for solving first order differential equations: separable, linear, exact, non-exact, and many others. So now we are going to discuss solution of higher order differential equations. Okay. In order to solve solution of higher order differential equation, we need this notation. Okay. And then in the subsequent lecture, maybe in the next lecture or today's lecture, you would see that this notation will help us. From this linear operator, we shall derive a polynomial of the same degree of the same nature. And then we shall try to find the roots of that polynomial. Okay. So this d will be replaced by some other variable, some other maybe parameter, okay, which will result into a polynomial of same degree, and then we shall try to find the roots of that polynomial in order to solve the higher order differential equations. I hope you get something, and you will understand in the upcoming lectures, maybe today's lecture or tomorrow, next lecture. And there are many other applications of operators in courses, in advanced courses of differential equations. You might take the course of ODE, which is math. I think it's not 210, it's 341 or something. It's a course of ordinary differential equations. That is an advanced level course of differential equation. In that course, we introduce operators properly and we discuss them. Many kinds of operators which have different applications. Okay, so this is just you can say the basic introduction to operators. Okay, for now it's sufficient, I think. Next thing, is the linearly independent. No, before that, we are going to discuss superposition principle. Superposition. Superposition principle works only for the homogeneous ODEs. Remember this. It works only, or it is valid only for homogeneous ODEs. Okay, it is not valid for non-homogeneous. What is this principle? Students who have taken LA with DE, they might know already, but let me introduce it. Superposition principle is the principle. Let us say we have a differential equation of nth order, okay, homogeneous. Let L of y is equal to 0 be an ODE of nth order. Okay. And it is also linear in our case. Linear ODE of nth order, then, and let y1 of x, y2 of x, yn of x are n solutions of given nth order ODE, given ODE. But the equation should be homogeneous, okay? Homogeneous ODE. Remember this. If we have nth order differential equation, homogeneous, because I have put here 0. If it has n solutions, then the linear combination is also a solution of the given differential equation. Okay. Then in general, y of x is equal to c1 y1 of x plus c2 y2 of x plus so on plus cn yn of x is also a solution of ODE, of the same ODE which is given. This is what we call principle of superposition. If we have, for example, if we have a second order ODE and it has two solutions, then the linear combination is also a solution of the given differential equation. I hope you know what is a linear combination. Linear, this is what this is how we write a linear combination of n functions. So these are in fact n functions, which are solutions of the given nth order ODE. If we have n solutions, then this is how we write the linear combination of n functions. Okay, it will give us another function. Okay, this function will also be the solution of the given differential equation, and it is called general solution of the given ODE. It is called general solution of the given ordinary differential equation, which is homogeneous. For example, let me go to the other board. For example, the functions y1 of x is equal to x squared and y2 of x is x squared times log of x. Be the solutions of the following ODE: x cube y triple dash minus 2x y dash plus 4y is equal to 0. 0, 0 means it is homogeneous equation. On the interval 0 to infinity. Okay. Now these are two solutions of the third order homogeneous differential equation. Then by using principle of superposition principle, then by principle of superposition, the linear combination y is equal to C1 y1 of x plus C2 y2 of x means C1 x squared plus C2 x squared log of x will also be a solution of given ODE. Okay. Another thing important, homogeneous ODEs always have a trivial solution. Trivial solution y is equal to 0 is always the solution of any homogeneous differential equation of any order. Okay? Remember this. Now, there are a couple of other examples included in the notes. You can see them. The next thing is we are going to discuss fundamental set of solutions. Of an ODE. Of an ODE. In fact, it should be homogeneous. If we have, let L of y is equal to 0 be an ODE of order n. And y1 of x, yn of x be a set of n solutions of the given ODE. Then the set, this one, y1 to yn is called fundamental set of solutions. If this set is linearly independent, if this set is linearly independent, how to check whether this set of n functions is linearly independent or not? I hope you know it in linear algebra. Okay. If you don't know, anyone, this course has a prereq as linear algebra. So I hope you can, and you remind what is the set of linearly independent functions. There are two ways of verifying whether the set of n functions is linearly independent or not. If we are given, for example, what is the basic definition of linearly independent? What is the definition of linearly independent or dependent? Linearly dependent or independent functions. Independent functions. If we have n functions, for example, a set of n functions, maybe f1, f2, so on, fn, if we have n functions, and we have to prove that this function is linearly independent or dependent, then what we do, we consider the following expression: C1 f1 of x plus C2 f2 of x plus so on plus Cn fn of x, and we put this expression equal to 0. And we try to find these constants out of this expression, this equation, okay? We try to find C1, C2, Cn, okay, using this expression. If at least one of these unknown constants, C1, C2, so on, Cn, if at least one of these constants is not equal to 0, then we say that the set is linearly dependent, okay? What do we say? If at least one of C1, C2, so on, Cn is not 0, then the set what? F1, F2, so on, Fn is linearly dependent. Okay. for any value of x. Okay, if it is not zero, at least one of these constants, if it is not zero for any value of x, then the set is called linearly dependent. Otherwise means if all C1, C2, so on, Cn, they're all zero for any value of x. Otherwise, the set F1, F2, so on, Fn is called linearly independent. I hope now you remind this concept from the LA with DE. Normally, all the instructors teach this in the LA with DE course, MATH210. Let's have an example of this thing. There are several ways of proving whether the given set of functions is linearly independent or not. I have included a couple of examples in my notes. For example, maybe let we have f1 of x be x, f2 of x be x squared, and 4x minus 3x squared. And another function f3 of x is 4x minus 3x squared. Okay. Now we need to check whether these functions are linearly independent or not. Okay. How to check it? We write that expression. We start by consider C1 f1 of x plus C2 f2 of x plus C3, because we have three functions to. So we write that expression for three functions. Now we put in these values of these functions, C1x plus C2x squared plus C3 times 4x minus 3x squared equal to 0. Now, can we, on observation, can you tell me whether all these constants, C1, C2, C3, they must be 0 for any value of x? Or can we find values of these C1, C2, and C3 so that their values are not 0, but this whole expression gives us 0? Are there any values of C1, C2, C3? Yes, C1. C1 should be, if we take C1 -4, और यहाँ पे +4, और C2 को हम ले लें, -3 है, यहाँ पे इसको हम +3 ले लें, और C3 को हम 1 ले लें. We can observe it. Yes. So there are values which are not 0, but still this expression becomes 0. So I told you, if at least one of these C's is not 0, then the set is linearly dependent. Okay. If all these constants are identically 0, then we say that the set is linearly independent. Let us choose another example. Maybe this one. Now I'm going to change the functions. See, F1 is 1 plus x. F1 is now 1 plus x, and F2 is x and x3 is x squared. X3 is x squared. Okay. Now, by considering this expression again, we are going to write C1 1 plus x plus C2 x plus C3 x squared equal to 0. Can you find some values of x? Some values of C1, C2, C3, which makes this expression equal to 0? Let us choose C3 0. Agar C3 को 0 लें, because there is no other term which involves x squared. Okay. So C3 must be 0. Then C2 and C1. What could be the value of C2 and C1? C2 को अगर आप -1 ले लें और C1 को आप 1 ले लें, ठीक है? C2 को आप -1 ले लें, तो आपका x वाली टर्म एलिमिनेट हो जाएगी, ठीक है? अब C1 रह गया, C1 को क्या लें? C1 ऑब्वियसली 0 लेना पड़ेगा. फिर x क्या हो जाए? x को डेफिनेटली x यहां पे C2 पॉसिबल नहीं है, -1. क्यों? चलें इसको, there is another method of solving this. Convert this expression into this C1 plus C2 x plus C3 is equal to 0. Sorry, C3x squared. We have collected the coefficients of like powers of x. Now, by comparing left hand side to right hand side, we can write what? C1 is equal to 0. C1 plus C2 is equal to C1 C plus C2 is equal to 0 and C3 is equal to 0. Comparing, because we can write here 0 plus 0x plus 0x squared. Now, this is what? This is homogeneous linear system. And homogeneous linear system can be solved by writing it into augmented form and then reduce echelon form or echelon form, and then we can solve it. If C1 is 0, we put it here equal to 0, then C2 also becomes 0. So C1 is 0, C2 is 0, C3 is 0. We cannot find any appropriate values of C1, C2, and C3 here, which are not 0, but they convert the given expression into 0. Okay. So we are unable to find any value of C1, C2, C3, which are non-zero. All values must be 0. So these three functions are linearly independent because all the constants are identically 0 for any value of x. So therefore, this set is linearly independent. But this method is basically lengthy and difficult while you use observation or you try to solve this expression in this way. And in addition, if I change this function to maybe exponential of x, then how would you compare and how would you obtain a linear system, homogeneous linear system? It is not possible in that case. So we must have some other method which help us to find whether the given set of functions is linearly independent or not. And that method is the method of Wronskian. Wronskian gave this method which help us to easily compute or to know whether the given set is linearly independent or not. Okay. So if the set of n functions is given f1 of x, f2 of x, so on, fn of x, then how do we compute Wronskian? In fact, Wronskian is a determinant of what? We call it W of x, and it is the determinant of a matrix whose first row contains f1, f2, f3, or f1, f2, so on, fn, only the functions. Second row contains its first derivative of all the functions, and so on, and so on, and so on. And the last row contains its n minus 1th derivative, okay? N minus 1th derivative of f1 of x, n minus 1th derivative of f2 of x, and so on, fn minus 1th derivative of fn of x, okay? So this is the Wronskian. Provided that all the functions f1 to fn have n minus 1 derivatives. Okay, means the set of functions, each function in this set, it should be differentiable up to n minus 1th order. If it is not, then we cannot compute Wronskian. For example, n, the domain of n minus 1 derivatives over the domain, whatever the domain is, maybe it is, we call it D or an open interval A to B, okay? It should be subset of R, or it could be R as well. For example, if we are given some function, f of x is equal to square root of x, and the domain is what? It is minus 1 to 1. Then this function is not differentiable on this domain. Why? Because if we take its derivative, it comes into denominator. The x goes into denominator. And in the denominator, for x equal to 0, that derivative does not hold. Okay, so that is why we make sure here that all the functions, they should have n minus 1 derivatives on the given domain. Example of that is this, this function is not differentiable on this interval. Because why? If we take its derivative, x goes into the denominator, and in the denominator for x equal to 0, which is in there, this function is not differentiable. So you have to be sure that all the functions have n minus 1 derivatives. Then we can try to find the Wronskian of those functions. If the Wronskian is not 0 for any value of x, after computing Wronskian, if W of x is not 0 for all x belongs to the domain AB, for all, it should be not equal to 0 for all values of x, then the set f1, f2, so on, fn is linearly independent. Okay. If the Wronskian is not 0 for any value of x within the domain, then the given set is linearly independent. Okay. Now let's try this concept on these three functions. The function originally here was x, I think, yes. Now try to apply this concept on these three functions. I hope you would have written this, or maybe you understand it. Now, if these are three functions, they have infinite many derivatives. They have at least two derivatives. How many functions are there? We have three functions. So all these three functions, they should have at least two derivatives. Because here, how many functions are there? N. So they should have n minus 1th derivative. Means n minus 1. So here we have three functions. They should have two derivatives. All the functions have two derivatives? Yes. f2 of x, या f1 of x, इसका second derivative क्या होगा? 0. So 0 is still a valid derivative. It exists. So we don't worry about it. So the Wronskian is what? Wronskian is, in this case, it is f1, f2, f3, f1 dash, f2 dash, f3 dash, f1 double dash, f2 double dash, and f3 double dash. So what it will be, 1 plus x, x squared. Its first derivative is 1, 1, 2x, and 0, 0, 2. This thing. Now, what is the value of this determinant? You can try any technique of how to find the determinant, which you have already studied in LA, linear algebra course. So you would see that the value of this Wronskian here, whatever it would be. मैंने यहाँ पे नहीं किया। आप सेकंड रो से या सेकंड कॉलम से या फर्स्ट कॉलम से करें? हाँ, थर्ड रो से कर लें आप, तो -2 आ जाएगा। -2, 1 plus x, x, 1, 1, लास्ट रो से। So it is -2 and 1 plus x minus x. This thing, and it becomes minus x plus x cancel, and we get -2. यहाँ पे हाँ 3 plus 3 plus 1 होगा, 3 plus 3. Yes, so it is plus, it is plus. So it is not 0 for all x belongs to R. ये x की किसी भी वैल्यू के लिए 0 नहीं हो सकता, क्योंकि x है ही नहीं इसमें. So the Wronskian is not 0 for any value of x. If the Wronskian is not 0 for any value of x, then this set of functions is linearly independent. I hope you get it. If you have any question, you can ask me. Now, come back to this fundamental set of solutions. What is the fundamental set of solutions? So if these three functions are solutions of some third order differential equation, homogeneous third order differential equation, then this set will be a fundamental set of solutions. Okay. And the general solution, and the solution which is basically the linear combination of these three solutions, will be called general solution of the given homogeneous differential equation. You can see all these things in my notes. Okay. Here is an example of fundamental set of solutions. Let me go here. Example. Given ODE is y double dash minus y dash minus 12y equal to 0. Homogeneous ODE. Prove that the set e raised power negative 3x and e raised power 4x forms a fundamental set of solutions and write the general solution of given ODE. Okay, since this differential equation is of second order, so we can have two solutions. Okay, how to prove that this is fundamental set of solution? We need to prove that this set is linearly independent. Okay, so we need to prove here. We need to prove that the set e raised power negative 3x, e raised power 4x is linearly independent. And how do we prove it? We cannot prove this set to be linearly independent by considering that expression C1 e raised power minus 3x plus C2 e raised power 4x. And by putting it equal to 0, we try to find the values of C1 and C2. We'll never have these values because the functions are not the obvious functions. They're not polynomial functions. They are exponential functions. So this method will put us in a difficult situation to find C1 and C2. So we don't use this method. We try to find the Wronskian, okay? The Wronskian of x is what? It would be negative 3 e raised power negative 3x, e raised power 4x, and their derivatives, okay? And the derivatives is 3 e raised power 3x, negative 4 e raised power 4x. Now, you can see that this Wronskian is non-zero for any value of x belongs to R. It means that these two functions are linearly independent and the set forms a fundamental set of solutions. Okay? If this forms a fundamental set of solutions, then the general solution is y of x is equal to C1 e raised power negative 3x plus C2 e raised power 4x. So this is our general solution of the given ODE. Wronskian में n-1 तक होता है ना? Wronskian में n-1 तक डेरिवेटिव्स जाते हैं यहाँ पे. Any question? So this is how we can write the general solution of the homogeneous ODEs. Okay. If you have any question, you can ask me. Now let us discuss the higher order solution of higher order ODEs. Now we are in the position to discuss the solution of higher order ODEs, but a special case of higher order ODEs, not all. And as well as homogeneous. I told you in the previous lectures that differential equations are not easy to solve analytically. This is what we are discussing, how to find the solution of a differential equation using some mathematical methods or procedures or some algebra. Okay, these methods are called basically analytical methods. Okay, solving higher order ODEs. पहले हमने फर्स्ट ऑर्डर किया था सॉल्व करना. Now we are going to learn how to solve higher order ODEs, but not all kind of higher orders. First of all, the equation should be linear. Okay. The first thing for now, what we are going to discuss, how to solve linear nth order ODE, linear homogeneous nth order ODE with constant coefficients. What we are going to discuss first, how to solve linear nth order. One thing, second thing, linear nth order homogeneous ODE with constant coefficients, not the variable, constant coefficients. Okay, remember this thing, constant coefficient. That is important thing. Now, what is that equation? Nth order linear homogeneous ODE with constant coefficients. How can we write it? We can write it by, चलें, L में नहीं लिखते, directly लिखते. A n of x हम लिखते थे y d n y by dx n, यहाँ पे यूनिक n आएगा, ठीक है, प्लस a n minus of 1 of x dn minus 1 of y dxn minus 1 plus so on, plus a2 of x d square y by dx square, okay, plus a1 of x dy by dx plus a naught of x y equal to 0, because we are going to discuss homogeneous. Now, these coefficients, they depend on x. They are variable coefficients. They are functions of x. Okay. They are functions of x. They are variable coefficients because they depend on x. Now, what we are talking about, constant coefficients, that these coefficients of the derivatives of y, these coefficients, they must be constant. This one as well. Okay. So this equation in that case will be written as a n dn y by dxn. Sometimes we write it, this thing, nth derivative, in this way, yn plus an minus 1, yn minus 1 in the brackets, maybe, plus so on, plus a2 y double dash plus a1 y dash plus a naught y equal to 0. So this is our equation 1 and this is our equation 2. Now what we are going to discuss, how to solve 2 still. Okay, how to solve nth order linear homogeneous ODE with constant coefficients, where all these an, n minus 1, a2, a1, a naught, these are all constants. where you can write here, where an minus 1, so on, a2, a1, a naught, they belongs to R. Means they are some real constants. They could be any constants, plus, minus, fraction, anything. Now, our problem is to how to solve this differential equation. First of all, we are going to discuss second order, first order, second order, and then third, fourth, and we will generalize this concept. Case one, maybe. Yeah, not case one, order one. If that equation has order one, what is this? A1 dy by dx plus a naught y equal to 0. This is first order linear homogeneous differential equation with constant coefficient. Or we can write it in this way, a1 y dash plus a naught y equal to 0. This is separable as well as linear. Okay, you can solve it by any method. Y dash is dy by dx. Then how can we write it? Maybe you can say dy by dx is negative a naught by a1 y. Okay, and then dy is what? 1 over y equal to negative a naught over a1 dx. Right? Integrate both sides, we get natural log of y, and here negative a naught over a1x plus c after integrating. Now we have log of y here. We can write y is equal to e raised power negative a naught over a1 x plus c, and we will have some constant here, c, as we solve the first order differential equations. So the form of the solution is the form of solution is what? Y is equal to e raised power mx, where m is what? Negative a naught over a1. M is what? Negative a naught over a1. So this is the solution of the first order linear homogeneous differential equation with constant coefficient. Remember this. Okay, it's a general form. Its constant multiple is also a solution because of the superposition principle. But we are not taking here the constants. We are going to generalize this concept. Now, if you put this solution here in this equation, you would see that you can find this, the value of m in this way if you forget about this method. Okay. Now, we assume that the second order, in case of order 2, also, the equation is a2 y double dash plus a1 y dash plus a naught y equal to 0. We don't have any method for solving this equation still. We don't have any method. So we haven't discussed second order differential equation, how to solve them. We are going to generalize this concept. What is this concept? We know that the solution of first order differential equation is of this form with an unknown value of m. If we put it here in this equation, forget about this solution. Now, you know that the solution of this differential equation is of this form. Now put it here what do you get? A1, derivative of this thing is what? M e raised power mx, this plus a naught e raised power mx equal to 0. You can take common here e raised power mx, and you can have a1 m plus a naught equal to 0. If you put that solution here in this equation, you get this expression. Now, the product of two functions, this and this, is equal to 0. Now, this function cannot be 0. Why? Because it's exponential function, and exponential function is never 0. What does it mean? It means this implies that this function must be 0. ma1 plus a naught equal to 0. Now, what is this? This is a polynomial equation in m of degree 1. This is a polynomial equation of degree 1 in m with constants a1 and a naught. How to find the root of this equation? It's simple. You write m is equal to what? It is negative a naught over a1. So we get the same value of m, which we have obtained here, minus a naught over a1. So our solution will be y is equal to e raised power negative a naught over a1 times x. Okay. So if we insert this solution back into this equation, we in fact obtain a polynomial here. If the equation is of first order, we get a polynomial of degree 1. And after solving this, after finding the roots of this polynomial, we can have the solution, this thing. Now we are going to generalize this concept for the second order differential equations as well. We assume that y is equal to e raised power mx is the solution of this differential equation, which may be 1. This is, assume that this is a solution of 1. If we assume this, then we have to insert this back into this equation. And then we try to derive a polynomial here, and we'll definitely obtain a polynomial of degree 2. In this case, in m, we'll obtain a polynomial of degree 2 in m. Variable will be m. And after solving that polynomial of degree 2, we can have 2 roots, at most 2 roots. Okay, let's put it in this equation, and then we'll see what happens. So the equation is a2y double dash plus a1y dash plus a naught of y equal to 0. So if we put that thing is here, a2, and second derivative of e raised power mx is what? It is m square e raised power mx plus a1. One derivative is m e raised power mx plus 0 derivative is e raised power mx equal to 0. Now we can take common e raised power mx, and we can obtain what? A2m square plus a1m plus a naught equal to 0. Now this is the product of two functions which is equal to 0. And the left-hand side function, this e raised power mx cannot be 0. E raised power mx cannot be 0 because exponential function is never 0. So this function must be 0. This implies a2m square plus a1m plus a naught equal to 0. So this is what? This is a polynomial of degree 2 in m. Now, this polynomial can have at most 2 roots. If it has 2 roots, then we can have 2 solutions. For example, this polynomial of degree 2 has 2 roots. M1 is maybe alpha, and M2 is maybe alpha 1 and alpha 2. They have 2 roots. depending on its discriminant is either greater than 0, less than 0, or equal to 0. Okay? The roots may be real and distinct. Their roots may be real and repeated. Their roots may be complex numbers. We'll discuss these cases after it. So if this polynomial of degree 2 has two roots, m1 and m2, which is alpha 1 and alpha 2, then by inserting the values of m here, we can have two solutions. Okay, we can have two solutions. The solutions would be what? Y1 would be what? E raised power alpha 1x, and y2 of x should be what? E raised power alpha 2x. So these are two solutions of this equation, second order linear differential equation with constant coefficients, homogeneous as well. If it has two solutions, two different solutions, now we check whether these two solutions form the fundamental set of solutions. We check whether these two solutions form the fundamental set of solutions of this differential equation. If they form fundamental set of solutions by checking whether they are linearly independent or not, if they form fundamental set of solutions, then their linear combination will also be the solution of this differential equation. Okay, what would be their linear combination? Their linear combination would be what? Y of x C1 Y1 alpha 1 x plus C2 e raised power alpha 2 of x. So then their linear combination is what? Is also a solution of the given differential equation. And this is what is the general solution of one of the given ODE. Okay, if we have two distinct roots of this polynomial of degree n, of degree 2, if the roots are real and distinct, then this will be the general solution of the given ODE. What is the given ODE? This one. Now, in case of order 3, we assume the same solution of the third order differential equation. We put that solution in that third order differential equation, and we arrive at a third order polynomial, third degree, a polynomial in n of degree 3, which might have 3 roots at most, which will have at most 3 roots. 3 roots only, you'll get 3 solutions. You'll get 3 solutions, y1, y2, y3. You check whether that set of solutions is a fundamental set of solution. Then again, you can write the general solution by writing the linear combinations. Okay? If you have fourth order ODE, then you will obtain 4th degree polynomial here in M, which will have at most 4 roots. You'll get 4 solutions. You can write the general solution by verifying whether the given solutions form the fundamental set of solutions, and so on. In general, what you obtain an nth order polynomial, a polynomial of degree n in M. So here plus so on plus a n m n. Okay, you obtain this polynomial, which can have at most n roots. Okay, and this polynomial is called auxiliary equation or polynomial. In some books they call it auxiliary, or in some books they call it characteristic polynomial. Okay. We call it characteristic polynomial. In case of order 2, this is your characteristic polynomial. Okay. After solving this characteristic polynomial, you obtain roots of this polynomial. Roots are basically equal to the degree of the polynomial. Okay, if you have nth order, nth degree polynomial, then you will have at most n roots, and you can have n linearly independent solutions. You have to check it by finding the Wronskian of those solutions. If there are n linearly independent solutions of the given nth order ODE, then you can write the general solution of the nth order ODE, which will be the n parameter family of solutions. I told you that if you have a second order differential equation, its general solution must contain what? 2 parameters. If a differential equation is of order n, then it will have n parameter family of solutions. Okay? That is also connected here. I hope you get it. If you have any question, you can ask me. We'll discuss roots of this polynomial in the next lecture. What are the possibilities? What are the cases of roots of this polynomial, and how to write solutions in different cases? Because the roots could be real and distinct, root could be real and repeated, roots could be complex. Okay, there are different cases for the roots of this polynomial. We'll discuss those cases in the next lecture. I hope you get it. If you have any question, you can ask me. That's it for today. If you have any question, you can ask me. That is what I told you, that in earlier lectures, we discussed that the general solution of any differential equation of any particular order. For example, if we have a second order differential equation, its solution, its general solution must contain 2 parameters. It should be 2 parameter family of solutions. Okay? अब यहाँ पे nth order differential equation है. It should contain n parameters. Then that will be the general solution. ठीक है? अगर आपके पास सेकेंड ऑर्डर डिफरेंशियल इक्वेशन है तो उसमें 2 पैरामीटर्स होने चाहिए. वो कब हम इंट्रोड्यूस करेंगे? जब 2 लीनियरली इंडिपेंडेंट सॉल्यूशन होंगे, उसका लीनियर कॉम्बिनेशन लिखेंगे तो 2 पैरामीटर्स आएंगे. ठीक है? वो 2 पैरामीटर्स क्या है? बेसिकली दे आर कांस्टेंट्स ऑफ इंटीग्रेशन. ओके, so we must have a 2 parameter family of solutions for the second order, and this fundamental set make it sure that you have n parameter family of solution for the nth order differential equation. You don't have n minus 1 parameters, or you cannot have n plus 1 parameters. You must have exactly same number of parameters as of the order of that differential equation. Definitely. Will not have linearly independent set of solutions. Okay. अगर fundamental set of solutions नहीं होता, if we don't have fundamental set of solutions, we cannot write general solution. Okay, general solution must be written as a linear combination of linearly independent solutions. Otherwise, we cannot have general solution. ठीक है? Any other question? If you guys don't have any question, let me finish this meeting.